Hi, my name is Natalie Calvert, and this is Lab 3, Magnetic Field of a Bar Magnet. Introduction. The purpose of this lab was to try and find the magnetic field of a bar magnet by using a magnetometer app and taking various distances away from the bar magnet. We also had to compare our 45-degree computational data to the 45-degree computer program data. We also had to use the distance dependence of magnetic fields and the Biot-Savart law to find the magnetic moment of the bar. Some fundamentals were using a bar magnet, which represented a magnetic dipole, using Biot-Savart's law, and using the distance dependence equation. Down here we find the magnetic moment, which was 2.25, and n, which was the slope of our linearized data in the Excel sheet. Here's our model. We assume that the bar magnet acts as a magnetic dipole to be able to use the Biot-Savart's law, and here's a representation of that. Here's a list of materials you'll need. Most of them you already have, but some of them you need to get, like the app and the bar magnet. For the experiment/procedure for our system, this included the bar magnet, and then for the surroundings, this included everything but the bar magnet. For the initial conditions, we started with a bar magnet and a magnetometer app that was far away from any devices that could affect it. For the experiment, first we located the north end of the phone and the correct net magnetic field. We then started with pinpointing the magnetometer chip within the phone by sliding it up and down and back and forth, finding the maximum value, making sure to keep this steady so the north end is in the correct place. Then we took measurements of several distances away from the bar magnet, recording the x value of the magnetic field. We then took the phone an off-axis distance for the bar magnet several times while recording the x, y, and z values. In the bottom section, we have the linearized data that we got from taking 3 trials of multiple sets of distances on axis from the bar magnet. We had to take the log of the averages of all the numbers in order to get a more usable slope equation. There you can see the equation y equals mx plus b, where n is negative 3.04 and ln of k is negative 14.6. The top set of data is the off-axis field, where we took 3 trials of off-axis numbers and got an average net magnetic field that is 45 degrees from the bar magnet. We need to keep in mind that we subtracted our on-axis y component from the off-axis y component to take account for the Earth. I used some data from the Excel sheet and then calculated the magnetic moment by using these equations: the parallel magnetic moment equation, the distance dependence equation, and the slope equation from the Excel sheet I just showed. I then found k by taking e to the negative 14 and got 4.51 times 10 to the negative 7. Then made the distance dependence formula and the parallel magnetic dipole equation equal to each other in order to solve for the moment, which ended up being 2.25. Some observations that I had was that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. To begin, we were given starter code. We started with our constants, then created code to represent the magnet. We put in our own magnet's magnetic moment that we calculated from the Excel data. We then created a magnetic dipole function on our own that calculated the magnetic field of a dipole. Next, we had some values to scale and distances to choose to make the visual work. We then set up the observation locations, 2 on axis and the 4 off axis. Next, for each of the observation locations, we calculated the magnetic fields of the dipoles and created arrows to represent these. We then had a separate piece of code to calculate the magnetic field 45 degrees from the axis. This also included our average perpendicular distance from our Excel data. Again, we had an observation location, then calculated the magnetic field and made an arrow from this value. Here's our coding results. We have each of the magnetic fields from each of the observation locations, and then the distance from the observation location, which is the 45-degree one, and then the magnitude of B at the 45-degree angle from the computed data is found to be 1.407 times 10 to the negative 5, which is somewhat close to our value, but I will show in the next few slides. For comparing the computation data and the program data, the 45-degree axis magnetic field calculated from the Excel computations was 5.56 times 10 to the negative 5, while the computer program data calculated to be 1.41 times 10 to the negative 5, which is a big difference, but it makes sense because the computer program data does not take into account the Earth. Some sources of error, some nearby electrical equipment could cause the magnetometer app to read incorrectly, bumping the phone changes the orientation of numbers possibly, and failing to line up the phone with north before starting could also cause problems in your computations. Session. What if I hadn't oriented my experiment to compensate for the magnetic north and had instead laid out a meteor ticket on an intermediate angle with respect to Earth's magnetic field? My results would have been less accurate because the Earth would have skewed a lot of my data. I would have had to account for the Earth in some other way. What if you were to stick two identical magnets together end to end and run the experiment again? I would expect all my data points to almost double in magnitude while the directions would stay the same. The stronger the field would be with more than one magnet. Conclusion. Using the Weierstrass law and the distance dependence equation helps to calculate the magnetic moment of a bar magnet with accurate results. Distance is a huge factor that changes the strength of magnetic fields, and experimental data versus computer program data can vary drastically when one doesn't take into account the Earth.